Sigmatropic rearrangements are rearrangements where a sigma bond moves. So there was a sigma bond in one place, that goes away, and there wasn't a sigma bond in another place, that appears. So that's what's happening in these sigmatropic rearrangements, and it's happening because of the overlap of the ends of these molecular orbitals. It's a common pattern in this whole chapter. So what you'd want to do is, in this type of a problem, they'll give you both the reactant and the product. And you want to look for the bond that's broken, like the sigma bond that goes away, and the sigma bond that appears. So if you notice, on the left side of this molecule, we have a sigma bond that disappears. This bond to that oxygen, that goes away. So I'm going to draw that in. Then, if you notice, on the right side of the molecule, we don't have a sigma bond here to start with, and we do have one there to end. So I'm going to draw that in green there. Now, it doesn't matter which of these structures you draw those in on. I'll do it on the right side just to show. This question is asking you just to classify the reaction. And to classify the reaction, what you do is you number you count how many atoms there are between the bond you are breaking and the bond you're forming. And you do that on both sides of the bond. So for example, on top, I'm going to write in purple, there's 1, 2, 3 atoms between the bond you're breaking and the bond you're forming. There's 3 atoms there. And then on the bottom, I'll write this in orange, you also have 1, 2, 3 atoms between the bond you're breaking and the bond you're forming on the bottom. And so this is classified, these sigmatropic rearrangements are classified in brackets. And inside of the brackets, you put the number of atoms on each side of the bonds that are being broken and formed. So on one side, you have 3 atoms. On the other side, you also have 3 atoms. And so this is classified as a 3-3 sigmatropic rearrangement. So you've moved sigma bonds around with 3 carbons on one side from the bond that you broke to the bond that you formed, and 3 carbons on the other side between the bond you broke and the bond you formed. That's it for that one. For this, it's the same idea. You want to look for where a sigma bond was broken, where a sigma bond was formed. So we can see that on this left side, we have a sigma bond to this hydrogen going down, and on the right side, you don't. So that bond was broken. I'm going to just write that in both of these structures. It really doesn't matter which structure you use, you should get the same answer either way. Also, if you notice, we have a bond that wasn't there to begin with, and then it was formed. It is there in the end, that sigma bond there. So I'm going to draw that in here. And next, what we want to do is count the number of atoms on each side of the bond that's broken and the bond that's formed. So on the left side, we have 1, 2, 3, 4, 5 atoms between the bond that's formed and the bond that's broken. On the right side, we just have 1, the hydrogen. And so these sigmatropic rearrangements are classified with brackets. And inside of the brackets, you put those numbers. You put the smallest number first. So on one side, between the bond that's broken and the sigma bond that's broken and the sigma bond that's formed, we have just 1 atom, the hydrogen. And on the other side, between the bond that's broken and the bond that's formed, we have 5 atoms. So this is classified as a 1-5 sigmatropic rearrangement. So you've moved a sigma bond around, and when you broke, between the one you broke and you formed, is one carbon on one side and one atom on one side and 5 atoms on the other side. And notice that all the rest of the molecule really doesn't matter. You could have a whole bunch of wild, crazy stuff all over here. It can be big and crazy and wild. It doesn't matter. Look at the bond that's forming and the bond that's breaking, and count the number of atoms between them on each side, the smallest number of atoms you can find.